Welcome to MSP lecture series on the chemistry of main group elements. This is 42nd lecture in the series. So, when I stopped I was discussing about hydrides of group 15 elements. So, let me continue from where I had stopped. Let us look into hydrogen azide and azide salts. I had given introduction about azides and nitrides in previous lecture. Sodium azide is an important starting compound. This is NaN3. So, this can be obtained from the molten sodium amide reacting with sodamide with sodium nitrate. Further treatment of sodium azide with H2SO4 yields hydrogen azide or hydrozoic acid HN3. Hydrogen azide or hydrozoic acid is a colorless liquid, melting point 193 Kelvin and boiling point is 309 Kelvin. It is a dangerously explosive material and it is also a highly poisonous. Aqueous solution of hydrozoic acid essentially a weak acid. So, here pKa for this one is 4.75 and of course, azide ion is isoelectronic with carbon dioxide. Okay. And let us look into hydrozoic acid structure. Okay. So, linear azide N3 minus can be formed by deprotonation of hydrozoic acid and is symmetrical with two identical NN bond with a distance of 116 picometer. Of course, azide ion is also called as pseudo halogen because of its similarities to halides. Okay. So, here it is 116 picometer, both are essentially same. In case of hydrozoic acid, this is 124, whereas this one is 113 and this angle is 114 degree. Okay. And this distance is NH distance, bond distance is 102 picometer. I did mention about pentazole ion reaction of HN3 with this hexafluorophosphate ion in hydrofluoric acid at 195 Kelvin leads to the formation of this pentazole. For example, so here one can use arsenic or antimony hexafluoride. So, I am using here antimony hexafluoride. It involves two steps. Okay. So, treating with liquid HF at 195 Kelvin and then warming to 298 Kelvin. It gives pentazole cation HF. Okay. And of course, if you take solid pentazole cation, it oxidizes NO, NO2 and Br2, but not Cl2 or O2. So, let us look into few of these reactions here. If you treat this one with NO2, it gives nitrogen. When it is treated with bromine, same reaction is repeated here. It forms 2.5 equivalents of nitrogen. Of course, here counter cation is Br2 plus. Similarly, on treatment with NO, so these are some of the reactions of pentazole ion. If you are curious to know the structure of pentazole ion, I had showed you in one of my previous lectures. Let me write again. Of course, one can write several resonance structures. I am not going to write all the resonance structures for this one. Let me write simply the structure. You can make an attempt to write all possible resonance structures for this N5 plus cation. So, if you see here, these lone pairs are intact here, and of course, here positive charge is there, here positive charge is there. So, here negative charge. Of course, here we have two lone pairs. So, now overall net charge will be for this one N5 plus. So, of course, you can start writing several other resonance structures. Let me write one more. Once after writing like this, you can see cationic and anionic ones. This is neutral and this is okay, and this is here. So, again you can clearly see N5 plus. So, you can write 4 more resonance structures. You can make attempt to write in a similar fashion. Now, let us look into the oxides of group 15 elements. As in group 14, the first element of group 15 stands apart in forming oxides in which p pi bonding predominates. That means, in case of nitrogen, p pi and its oxygen compounds, p pi bonding is very important. Let us consider some of these nitrogen oxides one at a time. So, NO3, which is an unstable radical, NO2 exists in equilibrium with N2O4, it is dimer. Reactions of nitrogen oxygen compounds that liberate or consume nitrogen are generally very slow at normal temperature and at a pH of 7. Okay. Now, let us consider dinitrogen monoxide N2O, it is also called nitrous oxide. So, one can prepare by decomposing ammonium nitrate. So, when ammonium nitrate is heated to 400 to 520 Kelvin, N2O is formed. Similarly, NH2OH, when it is combined with HNO2, it leads to the formation of N2O. Okay. Dinitrogen monoxide, that is N2O, has a faint sweet odor. It dissolves in water to give a neutral solution. And if you are curious to know the structure of N2O, this is how one can write. And of course, here it is 113 picometer, and it is little longer. One can also write this structure. We come across one important application of nitrous oxide, that is as a general anesthetic. It is also known as laughing gas, but its major use is in the preparation of whipped cream, and it is used commercially to prepare sodium azide. Let us look into nitrogen monoxide, that is NO. Nitrogen monoxide is made industrially from ammonia and on a laboratory scale by reducing nitric acid in the presence of sulfuric acid. Let me write down all these reactions for you. So, when ammonia is treated with oxygen at 1300 Kelvin using platinum catalyst, so NO is formed. NO can also be formed in this fashion. Okay. Or and of course, if you just look into this reaction, this is the reaction basis for a Brown ring test for NO3 minus. After the addition of an equal volume of aqueous ferrous sulphate to the test solution, cold concentrated sulfuric acid is added slowly to form a separate lower layer. If NO3 minus is present, NO is liberated and a brown ring forms between the two layers. The brown color is essentially due to the formation of iron complex, penta-aqua nitrosyl complex of iron. So, that is responsible compound is essentially penta-aqua nitrosyl complex. So, of course, NO is a plus. So, essentially iron is in +3 state. Because of NO is giving one electron, it appears like it is in +3 +2 state. Actually, iron is in +3 state. So, one of the oldest known reactions of NO is the formation of N-nitroso-hydroxylamine N-sulfonate, that is known since 1800. Okay. It is a very interesting one. That compound is O3SNO NO 2 minus. This is called N nitroso hydroxylamine N sulfonate. Okay. The structure of this one is interesting. Let me write the structure of this compound. So, this is nothing but N nitroso hydroxylamine N sulfonate. Let us look into dinitrogen trioxide N2O3. N2O3 can be prepared conveniently by treating NO with N2O4. Dinitrogen trioxide is obtained as a dark blue liquid in the reaction of NO and N2O4 at low temperature. That means temperature should be around 195 Kelvin. You should remember we have to do it at very low temperature. Okay. If temperature is raised, it will dissociate back to give NO and N2O4. Dinitrogen trioxide is water soluble and is the acid anhydride of HNO2, that is nitrous acid. Okay. So, if you remove the water, it gives anhydrous dinitrogen trioxide, but on addition of water it gives back nitrous acid. So, dinitrogen tetroxide is essentially a dimer of nitrogen dioxide NO2, and this one is always in equilibrium with the dimeric structure, that is S2O2 is always in equilibrium with 2NO2. Okay. The solid is colorless and is diamagnetic, consistent with the presence of only N2O4 species. Of course, melting point is minus 11 degrees centigrade. Okay. And dissociation of this dimer gives brown NO2 radicals. Solid N2O4 melts to give yellow liquid, the color arising from the presence of a little bit of NO2 in it. Of course, laboratory scale preparation of NO2 involves decomposition of lead nitrate. If the brown gaseous NO2 is cooled to 273 Kelvin, N2O4 condenses as a yellow liquid. Dinitrogen tetroxide is a powerful oxidizing agent which attacks many metals including mercury at as low as 298 Kelvin, and the reaction of NO2 or N2O4 with water gives a 1:1 mixture of nitrous and nitric acids. So, 1:1 mixture of nitrous and nitric acids. In concentrated sulfuric acid, N2O4 yields the nitrosyl and nitrile cations. So, let us look into the last one in the series, dinitrogen pentoxide. Again, dinitrogen pentoxide can be prepared by treating nitric acid with P2O5. That means, it is essentially an anhydride of HNO3. Nitric acid on treatment with P2O5 gives N2O5 plus H2O. Okay. So, N2O5 is a colorless ionic solid. Ionic solid means it is a combination of NO2 and NO3. Okay. Melting point is 32 degrees centigrade. Okay. This is highly unstable. It forms colorless deliquescent crystals, but slowly decomposes above 273 Kelvin to give N2O4 and O2. So, dinitrogen pentoxide reacts violently with water, yielding HNO3, and also it is a very powerful oxidizing agent. For example, N2O5, when it is treated with iodine, it forms I2O5. So, iodine goes to +5 oxygen state, plus N2 is formed. It indicates it is a very powerful oxidizing agent. You can see the structures of some of these oxides shown here. This is linear, N2O is also linear, whereas NO2 has a bent structure, N2O4 has this structure, and N2O3, this is how it looks, and this is N2O5, and this is N4O. Let us look into the oxoacids of nitrogen. One important acid is H2N2O2, that is called hyponitrous acid. H2N2O2 is known as hyponitrous acid. Okay. An aqueous solution of sodium hyponitrate can be made from organic nitrates by this reaction that I am going to write here. Okay. And free H2N2O2 hyponitrous acid is a weak acid, but it is a potentially explosive. It decomposes spontaneously into N2O and H2O. The trans configuration is kinetically the more stable and has been confirmed in the solid state structure of Na2 N2O2 5 hydrated. So, structure looks like this one. Okay. So, nitrous acid. Nitrous acid is known only in solution and in vapor phase HNO2. It may be again prepared in situ by treating barium nitrate with sulfuric acid. barium nitrite. So, it can be prepared by treating barium nitrate with sulfuric acid. Okay. So, whenever we need, it has to be generated in situ and should be used, and it is a weak acid, pKa value is 3.37, but is unstable with respect to disproportionation in solution. Let me write disproportionation reaction that destabilizes HNO2. Okay. And if you are curious to know the structure, this is how it looks like. Okay. And this is 117 picometer, and this is 143 picometer, and OH bond distance is 96 picometer. Okay. And this, whereas this angle is 111, whereas this angle is 102. Okay. So, let me stop here and continue discussion on oxoacids of group 15 elements in my next lecture. Until then, have a very pleasant reading of group 15 chemistry. Thank you very much.